So for this section of the talk, I'm just going to focus on the work I do. Actually, the work we have been doing, it ranges widely, but to make it fit into today's time schedule, actually I'm just going to focus on a very small segment of our work. It's mostly on templating, patterning of different surfaces. But actually, we have done nanomaterial synthesis. We do colloidal dispersion, the stabilization process. But our objective is a little bit different from what other people do. Our goal is to develop a water-based system, but the other feature is to have high solid loading suspensions. The reason we want to do that because eventually we want to convert our nanoparticle aqueous system into a dry solid component so we can put it into devices. And then from that process, we see if we have the high solid loading suspension, what are we going to do next? The idea is really to convert it from a liquid to a solid process. We actually developed a technique called freeze casting. Quite a few people are doing this kind of processes, but our focus is really on nanomaterials and how to make small features through freeze casting process, but I'm going to skip all this today. Another one is after we have formed this solid material, they are kind of fragile, they change over time. So we actually use the sintering process and make it into the final component. But during this microstructure transition, we have developed a 3D microstructure characterization technique for porous, complex microstructure changes. And actually, I have another big segment in my work. It's about energy materials. These efforts, they are not necessary in nano. Actually, most of the time they are not. And we have worked on solid oxide fuel cells and electrolyzer cells for many years by now. The idea is to understand the material interaction at really high temperatures. When I say high, I mean 800 degrees Celsius. For many hours, like thousands of hours. But as I said, today I'm only going to talk about how we do the patterning process on surfaces. So many of you, I think especially for people in chemistry, this is nothing new. This is a process called anodization process. Basically, you put your material in an acid solution, and then you apply a little bit of current to it. And then you can create these pores in metal surfaces. The most common material is aluminum. You start out with metals, and then under the electric field, these pores start to forming on the materials. And this actually became very popular about a decade ago. It's called self-organized process because these pores, if you apply the condition right, they automatically form this hexagonal structure. And we have done this for different conditions like this one. It's for different acid. By changing the acid in your solution, you can change how large the pore is and how far apart these pores are. But fundamentally, they are all hexagonal structures. And so when I started this work, I said, okay, can we do something different? Even though it's hexagonal, but you only get one kind of arrangement. Another issue is these processing windows are very, very narrow. You got to be very careful. If the material has certain defects or the processing condition changes, you get a very random arrangement of pores and very different sizes or even different shapes of pores. To get this kind of arrangement, they are mostly confined in very small areas and oftentimes very hard to do. So the idea we have was to start out actually with some guidance for this patterning process. The guidance we provided was through the focused ion beam. So you have a metal foil, and then you bring this to the ion beam, and you start making some really shallow, very, very shallow indents. We call these concaves. And then from there, you bring it back to the lab, and then you do this anodization process, such as for this one, for phosphoric acid, we do it in acid under a certain current density and then different time. The nice thing about this anodization process is you can grow very, very long pores, like tens of microns, and then straight diameter. If you say, why don't I just use focused ion beam? Focused ion beam is great. But the problem is this beam has this Gaussian distribution. You end up with these kind of taper pores, and then you kind of go very deep, because when it's really deep, you bombard your material off, and then it's going to fall back in. So there are quite some limitation on this. So the idea is to have patterned pores, but then can grow very long. And with that, I just want to show you some of the things we want to do. So you might wonder this color picture, so I'll explain this first. This one actually is one of the patterns we created, and my student colored it up for the SEM pictures, just show you the capabilities. We are really not confined to the hexagonal spherical pores in many ways, but I'll show you more pictures as we go. So the idea is to overcome the inherent restraint from the anodization process, and be able to create a whole array of new features, such as non-hexagonal arrangement, non-spherical pores, heterogeneous pore size, and then really unique patterns. One example I'm going to show today is a more pattern, but you can do a Fibonacci and other patterns. It's like we did some other things like sunflowers. It's pretty versatile for this process. We not only want to change the surface arrangement, we also want to do a few things on the pore depth direction. We want to be able to split the pores and merge them later on, or create different features on the tube surface. Tube and the pore are two things. Like when these pores are connected in a matrix, we call them pores, but for certain materials, we can actually remove the connecting points, make them into long tubes, so that sometimes you see I switch between pores and tubes, but actually we just need to switch the matrix material to do that. And then the final goal is to use this as a template to fill in precursors, salts, and other liquids, so that we can create arrays of things. So with that, first to show you some of the capabilities we developed. This is the early on work. We actually, first thing we were able to do is to enlarge this pore-to-pore distance. As I said early on, through the kind of natural process, this pore-to-pore distance is very limited. So here we can start from 250 to about 500. We can still maintain regular arrangement of pores. This is still hexagonal, the early on process, but then when we enlarge the pore-to-pore distance, we start seeing some interesting things going on. I'll show you on the next slide what has happened. If we enlarge the pore even further, you actually start seeing new pore appearance. So this, like, you use a larger set of sites, but then you can create a new set of sites at these locations. And this is quite interesting, because now you start getting smaller pores. They are arranging in a very nice way. Not only that, because of this triangle arrangement, your pore, they are not spherical. They are triangular shape. And so this, for initially we got a hexagonal arrangement through the focused ion beam on the metal surface. All this work so far, it's on aluminum. It's not in the title, but it's on aluminum. So another really unique thing is we are not confined to the hexagonal arrangement anymore. You see here we have square arrangement of these patterns. And we can also create new pores at this actually quadral junction area, these 4 pores and then small pores here. And you will still have the limits. It's not like you can do in endless possibilities, but you get an enlargement of your processing window, but if you go too far, you start seeing like a random pore distribution like here. So this gives us possibility, but just be aware, we have enlarged the window. It's not like limitless process.
And those are all fully anodized?
When you say fully anodized.
Oh, well, what we're seeing on the surface is all aluminum oxide.
Yes, they're all anodized. I'm going to explain, like here, actually what you see here, they are all oxides, but you cannot tell the boundary, so it's one color. But then here you start seeing like this hexagonal outer layer is the oxide layer that belongs to this pore, and then this one belongs to this. You see the boundary for these oxide layers. That's why you start seeing like a cell structure on the surface. And the reason, but you probably already saw this, like this pore range, like these new pores at 500 nanometer, they are still regularly arranged, but for square pattern. At 500 nanometer, you start seeing random patterns. The reason is actually pretty simple. If we look at this is just a simple drawing for two scenarios. This first one, you see, when these pores are very close, these oxide layers, they overlap. You don't see the boundary because it has fully developed. But if you're at the right pore distance, these boundaries, they just overlap. And you start seeing that cell-like structure. And then when they are further apart, you have this possibility of creating a new pore. However, for the square arrangement, this pore distance, you're not looking at this direct distance, you're looking at the diagonal direction. So this distance is a lot further than this distance, so you start seeing the new pore appearance much earlier. And then when you have the same pore distance, you already have a big region here, so the new pores, you start creating more than one, and then they don't arrange nicely. So this actually goes back to the original anodization process. So we figured all this out, and I might go a little bit faster on this, but these are the fundamental process. Basically, for all the chemistry people, it's no-brainer. You actually have several layers. This is your liquid, the acid, and this is the solid. So in this liquid process, you have this Golgi-Chapman layer, you have this Helmholtz layer, and then when you get into the oxide layer, it's a major region that carries your voltage drop. And then when you go further out, if you still have metal, then this layer doesn't carry much voltage. But as this layer grows thicker and thicker, eventually the process is going to stop because it cannot anodize more of the metals here. So the electric field can be calculated by looking at the material properties like the permittivity and then the distance between the charge and then your point of interest and the accumulation of charge and so on. So we have looked at this, and we actually figure out how to calculate this, so we know the electric field at a certain location. So I will not go into the details, but you can use this cylinder model to assume like the inside is pure oxide as it goes. You actually don't have the Al2O3 structure. You also have some AlOH 3 type of thing because it's not really all, you have hydroxide. And then when you get here, it's more the metal oxide surface. So this X, we say, it changes from here to here. You have the highest oxide content at least here. And then you can calculate the permittivity and so on. So from that, another aspect to consider is the voltage drop. I touched upon this. So the total voltage drop is being carried over by these 4 layers. However, the oxide layer has a major voltage drop, and then at a certain point, your voltage drop across the oxide layer is about the same as your electric field, and that is the point where the pore growth is going to stop. So this determines how large the pore diameter you're going to get, how thick the oxide layer is going to be. So we have done this kind of calculations. And another thing we have done is look at the stress distribution, because during this anodization process, we have a few stress components. The first one is from aluminum to alumina, there is a volume expansion, a huge one actually. It generates quite high stress. Another one, there is chemical reaction going on, so you got temperature gradient, there is another stress. And then when we do the patterning process, actually the gallium ion beam is quite strong. It can change the aluminum from a crystalline phase to amorphous phase, so you got this. And the last one is we have a gallium ion implantation. So all these generate stress, but these actually already pre-exist before you even start the anodization process. These were created during the anodization. So we did some calculation and found out actually the major stress is from the volume expansion. So we can calculate, this is pretty easy to do. It's about 20% volume expansion. That's a huge amount. And then for the temperature, it's pretty minor. It's only 10 to minus 4. This is really the minor contribution to our system. And then implantation depth is only about 24 nanometer. And it's not much because we are really creating very thick layers, like a few hundred nanometer. So if you only have 24 nanometer, it doesn't really kind of determine the process. So the main driver for the pore formation and growth process is through volume expansion. So much for the details, and I want to show you some more things. Remember early on we were trying to change the pore distance so that we can create a set of new pores. But here actually what we can do is we can do it through the focus ion beam process, create a different size of pore. This is pretty easy to do using the microscope. So you see here we did some AFM measurement. We can see deeper pores and larger pores and small pores, shallower pores. We know that from the changes of these peak locations, we can calculate the pore distance, which we already know. But the idea to show you here is you can start with different size or depths of pores. You do an anodization process, they mirror the initial distribution. It's just an enlargement of the individual pores. You don't really disturb the patterns. And another way to show this is we actually can make pores large and small in different regions, not alternating pores, but large and small regions. We see these deeper pores and larger pores and small pores here, and then we do anodization. They maintain the distribution. So this really gives us a lot of capabilities to not being limited by the original uniform size pores, uniform size pore arrangement. Another interesting thing actually we realized we are not confined to spherical pores either. So these initially we pattern pores like this. This is kind of like unintentional discovery because the beam was not focused well. You see this elongated shape. And then when we actually anodize this, we got this elongated pore. You see the oxide layer in this picture is very, very clear. So this is interesting. We can move away. These are also not hexagonal. They are square arrangement. So this become quite interesting. And then we went back. Another interesting thing actually happened. You see I have the dimensions here. The major change we have made is to, during the patterning process, to make this long axis a little bit shorter. Just go from 150 nanometer to 100 nanometer. And then the interesting thing is we can create a set of new pores. And this set of new pores, they grow, the long axis direction is actually perpendicular to the original long axis direction. So this all actually goes back to a very simple reason, which is the oxide layer formation process. These pores, they are kind of in this direction. They are closer because they are longer in this direction. So the oxide layer for this small pore, it cannot grow in this way much. They are confined. So in this direction, these pores are further apart, and then the small pore gets more chance to grow in that direction. So as a result, you can create all kinds of pore distributions. This just show you the process. And from there, we actually found out that we have a whole array of new capabilities. So you see here we have alternating large and small pore, but you get an array of small pores. And here we can create large pores, small pores orienting kind of elongated in this direction, but then you get round pores, and you get elongated pore. Even though you start out with same size and shape pores, they end up differently. So you can do all kinds of design, but the idea here to show you the capability. As long as you can sit down, kind of pre-calculate how the oxide layer field is going to be, you can do so many things. And using this kind of template, you actually can do many, many novel component devices. So that's the whole idea. And you can even have the missing sites. This is like a little bit like purposely, not by increasing pore distance, but having missing pores. In the patterning, we start creating small pores, and then this is a different way of having missing pores, and then we create like this, and then this is more like a rectangle shape, and then we can create pores like this. So we can do all kinds of things from here. I will not spend too much time, but this is on the surface. And I mentioned the Moore pattern. Moore pattern mathematically is very simple. It's like this. You got two square things, and you got two square meshes, so you can overlap them, but there are different ways. One possibility is your two square meshes, they have different edge lengths. If you just put them on top of each other, you get one kind of Moore pattern. You can change the dimensions, and another possibility is to change you have two square meshes, but they have the same edge length. You rotate them. You let them lay on top of each other, but at a certain angle. So in this set of images, we actually changed this theta angle. You cannot change this to any random number. We can go back and look at the math book, but there are only certain angles you can change to get regular patterns. But we actually pattern these Moore patterns using fib, and then we came back to the lab, did anodization, and this is what we got. And then this is the other one. We changed the edge length from 350 nanometer, like one set, 400 nanometer for another. And then if you change it again, you change the pattern, give you an idea about what you can do here. The possibility is just endless to create these kind of patterns. To us, it's becoming a very straightforward process to do these things after some time. Now, so far I have talked about everything was done on flat surface. How about on uneven surfaces? So, because if we can do things on uneven surfaces, we have another whole new aspect to look at. So actually, we realized if we pattern this uneven surface, we can come back to the lab and anodize them. So the pores really grow along these kind of sloped surfaces, and no problem. You see, this is like a circular shape. This is more like a slope. This is a square with indents, and you have different heights. The lowest is around the diagonal direction, and so on. So this, you get a lot of ridges. We can grow these pores, no problem. So fib guidance is really a very strong function. It can really change your pore growth scenario. So more of this, just to show you, because we don't really always use the flat surface. So this kind of give you the potential for a lot of new patterning process to use this as a mode, like a master template, and later on create new components and devices like that. Now, so far we have looked at the top down. If we look at the side, if we are patterning the surface for these areas, we are not patterning. So how is the depth direction? So what we have found is actually your patterning process, because we have this amorphization process for the matrix, gallium ion implantation, and so on. We actually have biased the process. The pattern area, they tend to grow much faster. And because it grows much faster, it pushes the material away. So when this process, when these regions start to form pores, they are kind of lagged behind. So the pore here is it grows a lot shallower. Not only that, they get bent. So this first point is very clear, get much deeper pores, and then they bend. And actually, not only that, we also have a higher region because the expansion process during the anodization process. So this is our illustration showing why this happens. We still go back to the electric field concept. We say here the pores actually are growing, and this material, because this is a larger, very negative curvature here, and then the material here is not growing as fast, and the material expands, it pushes things away. We actually have papers, with all the mass and other things that I'll not go into the details here today, but we explained why and how this process happens in detail. And so we call this edgy effect. So if you have patterned and unpatterned area, you tend to have pore bending, and actually there are more things going on. Let me show you. So if you do it on an uneven surface like this, so for this we actually have a shallow pores. When we say shallow, we mean that the depth direction is pretty shallow. We have measured the distance. But you see at the beginning, because these pores, they tend to grow first. This is the patterned surface. This is after anodization, and this is the cross-section of the surface. So you see the pores, they tend to fan out, simply because the guided pores are so shallow, they grow first, they kind of fan out like this, and then they start growing straight. Now, if we pattern the pores deeper, not as shallow as this, we can actually use this to guide the pores to grow much deeper before they fan out. So we kind of know what we should do if we run into a situation like this, how to make the pores arrange. But eventually, if you have this concave surface, pores start to split. The individual pore, they don't split, but actually it's a distribution of pores. You start getting new pores through the center. So this image we did through the fib cutting process, you see some of the defects. So ideally, if the image can be done cleanly in the vertical direction, you should see these vertical pores, but sometimes they don't break evenly, or you get artifacts through the material deposition. You see some of these not so nice features, but actually the pores are going down, but they kind of merge and bend. We also can create a different pore depths. So this has been done before, but we are looking at this through a direction. We can make these pores deeper, these pores shallower, or vice versa. And then we can change the bending and the merging direction of these pores. Just the different ways of playing with this fib process. Now I'm going to switch the gear, because here we are actually relying on the fib and then relying on the surface topology to see how we are changing the pore distributions. But another one is we have not really changing the anodization conditions, right? So next I want to show you capabilities, what we can do if we forget about the fib. We come back, look at the electrochemistry, and there is this well-recognized relation between the voltage you apply and then the diameter of pores you create. So it has this linear relationship. And then, but our thought was, if we don't just look at them and know them, but we start changing this U, the voltage that we applied, what's the consequence? There are two ways you can decrease or increase the voltage. And if you, because this is diameter, if we want a pore to exist, we have to look at the surface area. There is this square root relation. So actually the key is you cannot just look at this linear relationship changing the voltage. You have to look at the square root relation to change the voltage. So to make the pores split or merge, you need to decrease or increase your voltage by square root relationship. This can be square root 3, 2, 4, and so on. And another trick actually is you cannot decrease your voltage randomly. I'll show you a picture on that. But you have to change it, follow this factor relationship. Now this is what we did. If we can, first if we decrease the voltage by this 1 over square root 3, we actually can split the pores, one pore into 3 pores. So this show you one big pore. Later on we can split them into, it's a lower layer. We can split it into smaller pores. And we actually found this quite exciting, because simply by maneuvering the relationship between applied voltage, we can split our pores. And then from there, a whole new array of abilities. Like here, we can change the voltage by decrease by 1 over square root 2. We can start split one pore into 2 pores. Change it by 1 over square root 4, which is 1 over 2. We can split it from 1 pore to 4 pores, 1 pore to 9 pores. So it's a simple change of applied voltage. You can do that. And another possibility is we can not just getting 2 layers of tubes or pores with these different sides. We can do it continuously. In the middle, we change this in 3 steps. And then we get pores like split 1 into 3, and then split each one of these into 2 more, and so on. So we call these branched pores, and we actually, the main rule to follow is the relationship between the voltage and the surface area. And here is 4 steps. We change from, the one point to say is, remember we are working in a voltage range. We cannot change this randomly. We have to make sure the pores are still formed. So this is within a range, and we can only change our voltage within that range. So this goes 2, 2, 2, and then we can create 4 layers of pores. So what's the consequence if we change this slowly? You can do that for some application like a catalyst and some bio-related applications. It's not a big problem. You can do that, and the problem is you don't get regularly distributed pore diameters. Like here, you got a random splitting of pores into smaller pores. You don't have these clean layers anymore, simply because the voltage is not controlled cleanly. And then we said, can we merge these small pores into large pores, right? So we are going in the opposite direction. And basically, we want to merge this N-size pore, can be 2, 3, 4, and so on, merge into large pore sizes. And we follow this relation. We merge the 4 pores into 1. So the drawing is here. And then we can do more layers. We actually can first split it, and then later on merge it again. So it's like playing some toys. You can change the way you want. So this is pretty exciting to us, because for a lot of systems, you don't always want straight one-size pore from the top to the bottom. Now another thing, I want to go back to the flat surface. We have these pores, but imagine some systems you want to put your device. You want to put your one species into these pores. Later on, you want to put a new species into these other pores. Or you want to have some in alternating distribution or different compositions. Right now, for these kind of patterns, you can't do it because it's all open pores. You have to fill them all. You have to do them the same way. But actually, our idea is to use the FIB to selectively close them and open them. So if we want to close these pores selectively, we just for illustration, I show you some of the bands. We actually can control this voltage and close these pores. This hole, they are closed, but leave these stripes open. And the key idea I just want to show you is, if you want to close the pores, you don't just go there randomly, turn on the beam. You actually need to go high voltage to close them. 30 kV is what we found. We can close this, and then we can selectively, this is just more illustrations. We choose this region, we want to close them, and then you see we actually did. We closed them. And sorry, I didn't get time to do the CUNY thing. Here is the VT logo. We can concentric circles, and then these things. We can do it pretty much any way we want. And then another thing I want to show you is, we have these closed and open regions, right? And then if we want to close them again, we can go back, close the whole thing. So it gives you the opportunity to close certain pores and then do something and then cover up the whole area. Now, how about opening it up back on? We can do that, but you need to know how to play with the FIB. The key idea is actually to lower the voltage. I mean, these are not just random numbers. We did it through different calculations and processes. Let's say we have a closed surface, right? You have pores or tubes underneath it. It's closed, but now we want to open this region. What we need to do is to bombard the surface with much lower voltage beam. And from there, we actually can open up the closed pores. And then now you can do a whole array of new things, like depositing these things, putting a new agent in, or putting new materials there. And we can also selectively, doing individual pores, 1, 2, 3, and so on, or very thin slice of pores. So the possibility, again, is endless as long as we know how to play with the FIB. So we can close the whole thing and we open it selectively. This is a Virginia map. Anyway, as long as you can import these images into FIB, it's not a problem. Now, we want to reclose some of this. For basically, we're just playing around. We use a high voltage beam. We close it, and then later on, here. Oh, these are the closed pores, and then we open it up, and then we close it again. So basically, we're just playing high voltage, low voltage. You can do this back and forth. So this, in the Z direction, offers a lot of new exciting opportunities for us to deal with really 3D materials. So the core idea, what's the core idea? I will not go through this. It's a lot of physics involved. Basically, there are two processes. If you use sputter erosion, use high voltage, you're really removing materials. If you actually do low voltage, you actually are closing it, but it's a slow redeposition of the bombarded material, and then there is a swelling process when the material is under the ion beam and the heat. And the atom actually also diffuse. We call those atoms add atom. Actually, eventually there is a viscous flow. We have developed the profile of the flow process. So if your sputtering process, the high voltage process, is greater than all these processes, you're going to open the pores up. If this process is slower, you actually are going to close the pores. So this is how you play. You can calculate and then see where things are. As I said in our paper, we have done all that. But for the time's sake, I don't plan to present those. But another thing we have played with is to change the surface of these tubes. We call them bamboo-like because they have these joints at different locations. So you remember the tubes actually were smooth during this merging, splitting, merging process. We have smooth tubes. But actually we can change our anodization voltage during this process, like high voltage to anodize it, and then lower the voltage suddenly so that the walls will grow like this, and then increase back on, go back to business like nothing ever happened. We can make tubes going in segments like this. These are connected species along the tube direction. So the simple change is just to kind of going through these voltage drops. So show you how the process goes. Again, all this chemical process, you got to work within the window. So if we just do very short time, this T sub 2 very short, 1 minute, you create a little bit joints here, and then longer time you create more. But if you keep increasing, you end up breaking up. You have these joints, but the layers start to separate at 3 hours. So these give you the possibility. You see, why do I need this? This can, like people have, say, try to increase surface area of the tube outer layer. That's okay. Just do that. And then.
Openings in the walls of the tube? Is that what we're saying?
Pardon?
So
Yeah, it's.
porous?
The tube walls are solid, but you can change the gap size in between the tubes. Some people, they are putting in different things in between the tubes. But also, if you look at this as a clean, nothing there, you get rid of all the things. There you can change the surface area to a certain extent, the outer surface area of the tubes. So just the different ways of, depending on the needs, you can change the system in different ways. So, and another way to change this bamboo type structure is to change the voltage. Remember early on in that slide we were changing the time duration here, but here we can change the voltage difference, the low voltage, how low do we want to go. We can change the structure in a similar manner, but just give us different views of things. So what do we do? I don't want to throw out a lot of applications. Actually, this work started from solar cell applications and so on, but here I want to show you some not very common applications in supercapacitors. I have to tell you it's a better material, but it's not the best material to apply these things to supercapacitors. So supercapacitor is something like, not like our a lot of things in our watches or toys. We not those conventional capacitor, but more is relying on the Faradic reaction. You can not just the straight two-plate, parallel plate charge storage, but through the Faradic direction, you can store a lot more energy. And then the challenge is to make sure you can have a long lifetime and you can store as much charge as possible. If you want to store a lot of charge, you need a very high surface area. So these tubes look like a good candidate. So we look at these things, and the tube direction also is one direction path. Hopefully it provides better charge transport and so on. So another thing we have done is we can treat these tubes because now they are hollow inside and then outside they are separate. We actually use the hydrogen treatment to create more defects inside the tube, and then show you like the charge storage capability. Actually, you still need the treatment to get this large square-like box, and the capacitance is higher for this. And then the most important, since it's oxide, it's very stable. You can do this 5,000 cycles. Basically, the capacitance stays the same. As I said, it's not the best supercapacitor material. There are many other things you can do, but it's not a bad material. So just some performance testing. The last thing I want to show you folks is we have created all these patterns, but our goal is to use it. So the easiest way to utilize them is actually to fill solid or precursor, fill liquids or precursors. If you fill solid, it's pretty hard. But through vapor adaptation, it's possible. However, if you have very long tubes, solid is the best approach. So these are some of the PDMS things we put in, starting from the monomers, the polydimethyl siloxane. And then we use a hardened one. That's why I said H. The idea to use hardened is to increase the rigidity of these rods so that they don't collapse and then bundle together. And this is what we got. You see the very straight rods standing out. And then this one is, actually this is top down. Top down actually is a much better way. It's not as pretty looking at this one, but it's a much better way to gauge the quality of your rods, because if you have any bending, you don't get such a nice arrangement on the top. So it has this triangular shape and it's very nice arrangement of the rods. So if you look sideways, they all stand up. So I'm going to show you some of these things we have done in our labs. So I don't know how I go on time. 8 more? Yeah. So the conclusion quickly is we can create a highly ordered tubes. So we can tune their arrangement, and then we can do it on a non-flat surface. We can we looked at the bifurcation, the termination part. We can do multiple layers with branched tubes, and eventually we can kind of close and open tube in different locations and so on. So our work over the years has been supported by all kinds of agencies, so that we can get graduate students into the lab. NSF, DOE, ONR. This is a large university consortium. They have, I don't know, more than 100 universities nowadays. This is from ACS, Petroleum Research Fund, and our university supported a lot of work. Some companies supported the effort. And got a huge group of students. I just named some of the people in the characterization facility, some postdocs and waiting scholars, some graduate students, a whole bunch of other undergrads worked in the lab now and then. But most of all, thank you very much for your attention. So
I think we can have a couple of questions now, and then if we have a little bit of time, we can maybe also talk to Casrc vision.
okay.
So, any questions?
How in terms of making pores and infiltrating with fluids, how deep can you go? How deep can the fluid infiltrate and into a pore before
Right. Yeah. Actually, the limitation is not on the pore filling process. That's what you're asking. Because we use a spin coater, we can fill pore, very long pores. Not a problem. The problem is when these tubes or rods get very long, you separate them, they actually start bending. That's the limiting factor. Actually, there is an equation we actually calculated. It depends on the material, so elastic modulus, and then the diameter of the feature. So depends. But like this, you can go like aspect ratio about 10, 20, not a problem. But if you go even longer, it becomes problematic. It's a material problem, not you can infiltrate it, not a problem. It's like after separation, they don't stay like like a steel rod. They don't go infinitely long. They just they bend. So that
made something that was very high modulus. Say if you infiltrated with a polymer that would have a high cross-link density.
Yes.
And became very high modulus.
Yes.
How deep could you go?
Like the PDMS, we actually started out with regular PDMS. It doesn't work. We have this; they all clump together.
Sure.
So we switched to a hardened PDMS. That's why it's called HPDMS. And this one, it can go. You see, like the scale bar there. It's about 500. Yeah, 500 nanometer. But if you want to make microns of this, I see it as very challenging because these things they bend. When they bend, especially when they are close, they get in contact. So this is the bottom, you can see. That's about the height. Probably that's the best we can do right now.
And when you separate, you're etching away the template, so the sacrificial.
We actually have also put TiO2 sol, the sol gel process is well known. We put TiO2 sol, and for this one, for the polymer, we actually just separate. For the sol, we dissolve away the titanium metal, and but then we still have the challenge of drying it because we dissolve it through the liquid. So we actually try the freeze drying because we have freeze casting process in the lab. Actually, it's still not enough. The way to go is critical drying process to really get rid of the liquid completely. Then you can get straight tubes. But even freezing the system and supplements of water is not. You already have during this washing process because this, like if we are infiltrating it, we got to wash it away and dissolving the metal, titanium, those features, they tend to already kind of capillary force and so on. They already are here to each other. It's not making them, it's about keeping them the way. That's the challenge. That's really the challenge for these things. Yeah.
Can you actually, once you have made these pores, can you take off the layer that's porous and use it for something else? Is it possible to separate it from the metal?
No, actually you don't. Taking it off is through kind of dissolving it. We can dissolve the base away. Yes. We actually I don't have time, but we have dissolved away the metal base and flip it over. Look at the back side; it's really pretty. It's all this semicircle. It's a tube, but it's a closed tube. You flip to the other side; it looks really pretty patterns. Yeah. There are to etch with a metal base, we use like a copper chloride and so on. But then to really open up the tube, if we have those closed semicircle caps there, you actually you can use vapor hydrofluoric acid. You open it up. So it just takes different process too.
So your structure that we showed was a set of tubes inside each other.
Yeah.
4 to 2 and 2 to 4. I think that would be great if you can look at them as members.
Yeah, these as I said, we are not, for people you're from chemical engineering, right? So that's why I say, need a collaboration with people in chemical engineering, sometimes mechanical physics. Yeah. For device use like solar cells and capacitors, and it's oftentimes they start getting into other areas. But anyway, it's just.
What other metals can you do?
Metals, it's not every metal you choose. There is a group of metals called a valve metal. Examples, aluminum is the most common, we all know that, and then titanium is the second, but then there is tungsten, some of even zirconium, I think, and then there are alloys of these things like a titanium vanadium alloy, you can do it. So there is a list, but it's this long, not that long. So there are some you can choose called valve metals.
It's the early ones that have high oxygen. It's the early metals that have high oxygen.
Most of them, not like, yes, somehow, but we kind of roughly know. But then, as to specific work, we need to look at the details. Yeah, but tungsten is another choice. People have not worked much on it. Nasty?
WO3 it's
oh, W.
non-stoichiometric oxides.
Yeah. I mean, people have worked on alloys, but the base is still the valve metal base.
Have you done any photonic studies on these?
Photonic study. We would love to know. I mean, I actually designed, the thinking was you have these rods. We actually have the ability to make them not like a sub-micron, like a 500 nanometer spacing, but actually lower. And then I have a whole bunch of ideas, but to make them kind of spacing a certain way, but not the same distance or not the same rod height, but different. And then we actually want to functionalize the rod surface, not just for photonic, but other responses. So it's a multifunctional material. But we have not gone that far. It's just we want to do, but in the back, go ahead.
When you do the opening and closing, can you do that with fidelity a number of times, or is there an end after which it's no longer possible?
We did not do like 10 times, but we can do 5 times, not a problem. The idea was to say people are doing like piezoelectric materials and like that. You want to fill it with nickel or some like barium titanate and so on. But you don't want your matrix to be alternating like that. We want to fill this, this pore, this one, that different, but also like at this height location, one material, different height, another material. So the thinking is to really being able to change the composition distribution, not in the lateral direction, but also in the longitudinal direction. And, again, if it's device level, we need to work with physics people, electronic people. It's we actually look at the sensor application of these tubes and so on. Yeah.
Any more questions? Thank you.
Thank you very much for your attention. So.
And so do you guys want to hear a little bit more about the SOC version? Yeah. So do you want to spend like 10 minutes on the other side?
Okay, you guys. Maybe I don't know if I'm gonna repeat to the committee or not, but
No, we are the committee.
different. You are the committee. Okay. Then I can go slide by slide. Not because I was thinking if there is.
I think Raymond might have still come. No, that's fine. I think.
Okay.
So I think during an interview you will have time to also rephrase your vision but without the slides. But just tell us a little bit about what you.
Okay. So not a problem. You guys are committed, but I was thinking how detailed I should go. I have
10, 15 minutes. Give us a general idea of what you want to do.
I have about 27 slides.
That's maybe a little long. Get the
Okay.
major message across. I think that's
Okay.
one of the ideas. And then I think in the interview we'll have time to go into more detail if you want to.
Okay, so in my opinion, I'm gonna go fast on this. Sometimes I tend to talk very fast, and it's hard for you folks to understand. But so the thought is, this gotta be a nice. I call it an institute because Advanced Science Research Center is a center, and under that umbrella there will be several institutes. You can give it different names, but institute is what I call it here. So the idea is to have a premier institute. Not just a so-so one. I don't like to do things, mediocre. I mean, oftentimes it turns out to be mediocre, but that's not our intent. Our intent is to do things the best we can. Then, so it's leading edge research. It's got to be interdisciplinary research. And then got to be transformative research. But in the end, it got to be sustainable. We don't want to do this for 3 years and then, let it die or something like that. So. As I said, the core idea, you guys are on the committee, so you have all these different thrust areas, but my view is to share the intellectual capital, share the resources such as the clean room and then the characterization facility, and even students, the manpower need to be shared. So this, we can go quickly. So there are some things is about philosophy and some about specifics. For the philosophy, I'll go a little bit fast. The idea is to serve different entities through high impact research, do true, high quality science, but interact with people in different disciplines, science, engineering, biology, and also with the focus on public education, because graduate students, they are an essential component of this process. And promote economic development in the long term. Actually, I moved my slide to later on, but I think I have some ideas on this, but probably won't have time to touch upon. So really increase the CUNY's reputation and capability in doing science. That's the whole idea. And establish a research culture so that we can really play a role on the national stage and further out on the international stage. But we can't just do one thing for 10 years. We got to be able to move things faster and then do things that we have not done before. Most important, we got to build different teams to make these things happen. And so it's about how to foster discovery, innovation, how to do out-of-box thinking, and how to move things beyond incremental improvement. And eventually, we need to actually go to a much wider scope. My experience, like you guys probably wondering, a lot of people say when you do sabbatical, why don't you go back to China? I mean, the past is there. I have a lot of connection there. But I actually choose Germany and go there. It's a very valuable experience. And we also need to manage our facility intellectual resources in a very responsible way, get the maximum out of it, and so that eventually we can store these for many years to come. That's called sustainability in my opinion. And so this is what I think the Nanoscience Institute should be. First, you have different focus from different faculty members, and then the knowledge-based, and then lead to a new discovery. But what we actually need is for the hardware, we need a lab support, and then we need computing facilities to do certain work. But eventually, it's the people that are making a difference. We need to have really dedicated faculty, and then active scientists and students, and then we have staff that can take care of this day-to-day operation of our facility and make the research go. And so these are some of the more specific things. Actually, I think yesterday after talking to Dr. Small, I think my scope is a little bit larger than what C envisioned. But the nanomaterial area is one area because you can't live without materials for all the disciplines. But then nanoenergy really is another area that we should spend the time and effort doing investing in that area. And then nanoelectronics. Photonic is close, but there are some things that we can do and look at the interface. And then nanobio is another area. And then emerging areas, somehow like say 3D printing we talked about today, and I talked with Dr. Trevino and other people. I actually personally published a few papers in 3D printing 7-8 years ago. Now it became active, so I said, people didn't do anything then. Anyway, So it's not, sometimes we cannot say exactly, but if we have a vision, we follow our vision, sooner or later those things will come. So for the nanomaterial area, there are all kinds of materials: metal, ceramics, polymers, semiconductor, biomaterials. So we need to strategically think about which areas we put first, and then be able to not only understand but also be able to develop a control matter at nano scale, like the presentation I have showed you. But then eventually we need to move these material-based knowledge and understanding capabilities to the device system level applications. This is where I see collaboration with like photonics and then making nano energy devices and so on. For the nano energy, there are a whole array of things what we can do. As I said, I have been working in the fuel cell materials for many years. We have worked in solar cells, not as extensive as this. We mostly focus on these dye-sensitized solar cells. But there are like organic solar cells, multi-junction solar cells. This is the conventional semiconductor effort. But with nano, in the wheel, there are a lot of opportunities to interconnect those things. And then this is a mechanoelectric energy device, like converting mechanical energy, like vibrations and so on, into energy collecting devices. And recently, actually, I started looking into some of the nuclear material applications, and we have a whole array of things. I think some are taking off. And then the storage device, I worked for battery companies, certainly know the important supercapacitors. We can do a lot of things, but I cannot do all these things by myself. This is just like what the possibilities are there for the institute. What kind of people we need to bring in to make these things happen? How to collaborate with fundamental science like physics and chemistry? How to work with device level people, like say nanoelectronics and device level for energy conversion. So so I have nanoelectronics here. It's about understanding the inter-atomic level interaction, quantum mechanic properties of material. Eventually, make devices using nanoscale species like tubes, wires, and even molecules to make them. And the idea is like quantum computers, even optical computers. I see a strong component of material discipline to play in this. And the nanobio interface, I myself is not a bio person, but tissue engineering. And I actually, in my class, students have common, I teach a material course called Advanced Nanomaterial course. So people come and go, they are trying to develop the best drugs for interaction with human body or kind of transport inside the human fluid, and tissue engineering and so on. So those are some of the things I think there are a lot of potentials to work with environmental people and bio people in this area. And there are some quite interesting emerging areas. As I said, additive manufacturing, like 3D printing is one. And nanoscale, like femtosecond laser, the interaction with materials, or high flux, high radiation flux, high heat flux of situation for the material behaviors. We call those materials in extreme environments. So these are the emerging areas. NSF recently set up one topic in this area. I don't know if you guys have seen that solicitation, but really eventually it's about how to go from fundamental science and then quickly move up to the component and then device level capabilities. And then I think there is a need to really integrate computation versus experimental approach. Nowadays, if you just rely on one, it's kind of weak. I myself is more experimentalist than a theoretician. So I kind of tuned down my my flowchart a little bit. I think this institute director, and then we really need somebody like associate director level, and then we need some assistant. Eventually, I know like the characterization facility like TEM, SEM, the idea is not completely jolted here, but we need some people to take care of those facilities so that it operates. And eventually, these people, they are not just sitting there. They need to go out. Like this branch of people, they would go out and they interact with people locally and nationally and internationally. Being active and also have a strong presence on the international stage and in their own communities. And this group of people, actually, they are really the glue in the facility to weave things together, really produce the results. But these need to be the leaders to make this happen. Quickly? Okay. So these are the people, like I was thinking, to really bring into the institute, the energy people, electronic people. I kind of tuned on this a little bit. If this maybe I should call it secondary. Eventually, we need to work with the existing faculty in the CUNY system. I know there could be some issues, but we need to really expand the graduate students. They are the people who are in the lab, who do the work. So different agencies we should go, not just the federal agencies, but also companies and the foundations and so on. And we need to have this multi-layer approach in proposal application, large-scale proposals, and then smaller-scale proposals. We need to have seed support from the institute, from the university, and team up with people on and off campus to make this happen. And a lot of things we can do. We can have grant writing workshops and peer mentoring groups, and can send our faculty to outside grant writing workshops. There are a lot of them. Encourage them for proposal reviews with the sponsors, and a lot of webinars from our sponsors. Or they have a lot of agencies. They have these pre-proposal workshops. We got to start from there. When we see the solicitation, oftentimes it's too late, and then we got to collaborate with our external colleagues in the community. So some of the things the institution can do is to put in seed grant. There might be some already, but we should look at the opportunity. Cost share, this is very important because a lot of grant opportunities require that. Grant supporting, writing support, that means there got to be some professional technical writers that help us put a multi-million-dollar project together. There are a lot of details that we can go into, but fellowships to help high-caliber students, attract them to the CUNY system. And then New York is such a nice place, New York City, to attract people. So convenient to have workshops, conferences, just bring people here, give them a look about our capability and our interest. We really need to utilize that aspect. And networking in the state, in the city, but also across the country in different ways. So this is one quick example about energy related. We can have a group of people working on energy storage, energy conversion, energy utilization, energy harvesting. We bring different group of people, but we also have graduate students. We also people who do energy, public education outreach in the policy aspect. So this is one example. We bring group of people to tackle on larger problems. And I'm going to skip this. This is about the graduate education. I have my own idea, but we are limited on time. And eventually, you want to form this multi-layer structure. Top, you have the faculty. Then you have visiting scientists, professors, and then postdocs, graduate, undergraduate, in some exchange students from other institutions or even other countries. So this, after you form this, actually you got a lot of flexibility to do different levels of research for different depths, so that we can tackle things more effectively. Diversity is big. I think in New York City we have a lot of opportunities on that. And this is just the philosophy of what we should have, as a working place. But eventually, this is my last slide. We really want to have a high quality science, and then we want to educate our students. And then we start off with nanoscale understanding fundamental science, but eventually through collaboration, we make device level things, and then we also need to have public education, not just policymakers, but the general public, so that we get strong support for what we do, and also we can have this sustainably for long term to come. So quickly, that's my
Okay.
my view on this.
Very much.
Yeah.